Okay, guys. So what we have to do today is, I guess we have to cover the review for the nodal analysis. Last week we did the review for the basic Ohm's law, resistance combination, mesh analysis, and stuff like that. So today we're going to review quickly nodal analysis, do some problems, and make sure you help me doing the problems. Don't just sit quiet and then see how I'm doing, but you're going to help me doing those problems. And then hopefully we will also be able to start at least Thevenin equivalent circuits. So as far as nodal analysis is concerned, and actually after nodal analysis, then we can do maybe a problem or two problems as which method is going to be the best, either nodal or mesh, for the problems that we have again discussed last week as well. Remember, the method that is best is the one that will give you least number of equations. Let's go ahead and okay, so this is going to be nodal analysis review. So let's look at a couple of circuits where we have to apply different nodal analysis in different ways. So let's just start with problem number one, which is simple problem. So let's assume we have let's call this maybe IX. IX. Let's say 10 milliampere maybe. So I'm going to combine basically two things here, that you have to determine what is the easiest method, and of course we'll have to calculate the power supplied by the source IX. Okay. All right, guys. So the first part, again, when you see a problem, you have to, in your mind, you have to basically analyze it. And in your mind, you have to determine what quantities do you know, what quantities do you need to know in order to get the quantities that you don't know. In this case, you need to know, of course, how much power is supplied by IX, and for that, what do you need to know? If you want to calculate the power supplied by the source, what is the quantity that you need to know or you need to calculate in order to calculate the power? It's the voltage across that IX, like we did, I think, in one of the problems last week as well. So we need to know what is the voltage across Ix? And once we have that voltage, then of course we can calculate the power supplied by Ix. So Vx is the quantity that is unknown in order to calculate the unknown power. That is our goal. Okay, so once you determine that, now there are several methods to find that Vx. The question is, what is the easiest method that you can employ to find Vx? And that easiest method is going to be nodal analysis. Nodal analysis is going to give you a single equation. And from that single equation, you can calculate the node voltage on top of R2 at the junction of R1, R2, and R3. Whereas if you apply mesh analysis, you have two loops or two meshes. So either you're going to find, if you're not applying super mesh, then you will have three equations. And if you're applying super mesh, you will have two equations. So in any case, you will have equations more than if you apply nodal analysis. So nodal analysis is the easiest method, and that's the method that we are going to employ. So we're going to go ahead and figure out what is the voltage at node A. Let's call this node A. And the voltage at node A, let's assign that by VA. Because if we have VA, then we can easily find Vx. Now, let me ask you this. If you know what is the voltage at VA, what will be Vx? VA and the voltage drop in R2. Very good. Or other voltage gain in R2, not drop, because the current that is passing through R2 is Ix in this direction. So the voltage here is higher and voltage here is lower. So you're going to add this voltage when you cross R2, then you will gain some voltage, remember, because this side has lower voltage and this side has higher voltage. So when you start at VA, so VA we are trying to figure out. Once we figure out VA, then we're going to add what into that? Huh? And that is? No, I know, but what will be the equation for that? From the circuit. Yeah, Ix times R2, because Ix is passing through R2, remember, right? So Ix times R2. So all these things are basically through your analysis. They're very easy, but you have to look at the circuit and you have to analyze it quickly as what will be the voltage that is going to be dropped or gained when you're going from VA towards Vx. So this is basically our goal, to find Vx. In order to find Vx, we'll find VA. And yes. Okay, so Ix is y. What is 0? Well, yeah, the ground is 0, but Ix is a current source, which is supplying current. It's an at VA. Why it's going to be negative voltage? Let's say I replace the current source by a voltage source. Then are you going to say the voltage source voltage is going to be negative if I have the positive polarity on top and negative at the bottom? Now, don't get me wrong. It is possible that the voltage Vx turns out to be negative. That's a different story. But when current source is supplying you the current, remember, this is an independent current source. It can supply current in the direction in which you're connecting the current source, right? So you have the reference voltage at the bottom. Current source is supplying current coming out from the top. So generally, the voltage at the top is going to be higher than the voltage at the bottom, because that's the potential difference in which direction the current is coming out of the current source, right? So if the current source, if I'm giving you the direction of this current source and I'm saying, or you're putting in lab, let's say you have a current source and you're putting in lab in this direction, you're assuming the current is going to come out from the top, right? It's not going to come out at the bottom, it's going to come out on the top. Now, if the current is going from bottom to top, is coming out from the top, it's going to pass through R2 in the direction from top to bottom. I mean, from bottom to top. that means when the current is going to pass through R2, some voltage is going to be dropped when it gets to the node A, right? Yeah. Well, that shows the direction basically, right? Direction shows that it's going up. Okay. So this is what we are looking for. To calculate Vx, we need to know Va. And to calculate Va, we are going to employ nodal analysis. And for nodal analysis, we assume a current. So let's say this current is I1, this current is I2, and of course we have Ix. So we're gonna apply KCL at node A. KCL at node. All right, what will be the KCL equation for node A? Yes, anyone? No. KCL equation, remember, give me the equation in terms of variables. What will be the KCL equation? Say it again. No. KCL does not have voltage. KCL simply says what? The current going towards the node, sum of current, is equal to sum of current going away from the node. That's KCL, right? Yes. Okay, she was going to. Yes, go ahead. No. So sum of all the currents going towards the node should be equal to sum of all the currents going away from the node. Look at the direction. All three currents are going towards node A, right? So it's going to be sum of all three currents should be equal to no currents going away from node A is equal to 0. Now, remember, these current I1 and I2 are totally arbitrary. You can choose any direction, but whichever direction you choose, make sure you write the KCL equation according to that direction. Now, in this case, I chose this direction that it is going, all these two currents are going towards node A. Ix is already going towards node A, that's given. But I chose I1 and I2 to be going towards node A. So that means all three currents are going towards node A. Now, if you choose I1 and I2 to be going away from node A, then yes, you will write I1 plus I2 going away is equal to Ix. So make sure it's upon you in which direction you are assuming the direction of current. They're totally random, remember, right? But once you choose the direction, stick with that direction and write the equation according to that direction, okay? So in this case, I have I1 plus I2 plus Ix, all three going towards is equal to 0. No current is going away. Michael, right? Your name is Michael? Yeah. Chris, okay, Chris, sorry. So now you're going to put what you were telling me earlier was the nodal analysis, right? So now you apply nodal analysis, but before you apply nodal analysis, make sure nodal analysis is applied on the KCL equation. So you have to write the KCL equation first to show which currents are going away, which currents are going towards, and then you apply Ohm's law and write the nodal analysis equation. So now you apply Ohm's law. What is I1? Vs1. Yes, go ahead. No plus. Vs1 minus Va over R1. Voltage at this side is Vs1, voltage at this side is Va divided by R1. That's Ohm's law. So Vs1 minus Va over R1. All right, I2. What is I2? No? Good. No. Yes. Say it again. V? No. You're going, that's not the direction of current. Nope. Why how many resistors are there in that branch? There are two resistors. Why you guys are considering only one resistor? You're considering only one resistor. There are two resistors in that branch, right? Now, remember, anytime current is flowing through a branch and it's the same current, what you can do, you can rearrange components. So I can bring VS2 down and I can move R4 on top, because you can always rearrange components if it's the same current flowing through a branch. It's not going to change anything, right? Because it's the same current. So you can rearrange components. So if you see something like this, and I intentionally gave you this so that you understand it. If you see something like that, the first thing that you, in your mind, you don't have to do it on the paper, but first thing that you do is you move the VS2 down and you take R4 on top of VS2. So R4 and R3 are going to be in series with each other. They are still in series with each other. They just don't, in your mind, they just don't look like they're in series, but they are in series. Yes?
Would there be a difference in the voltage drop between that?
No, remember, again, it's the same current, right? The branch, irrespective, how do you rearrange components in a branch? It is still carrying the same current. So from ground to VA, that's the same voltage if you calculate through that branch. It's the same voltage. VA is not changing, and the other end of that branch is grounded. So when you go around that branch, you will still calculate voltage, total voltage in that branch adds up to VA, irrespective how do you arrange those components, right? So if you're doing a lab, you put the resistor first, connected to the ground, then voltage supply, then this. It's still going to be the same if you move that resistor up and connect the voltage supply to the ground, because again, it's the same current, remember. If the current is split, if it splits, that's a different story, right? Then you'll have to consider how you are arranging components. But if it's in series, all the components are in series, you can rearrange those components whichever way you want. It's not going to make any difference, right? So keep that in mind. It's important because people get confused when they see something like, if I move VS2 down and give you R4, everyone will know what will be the equation. But I put this intentionally so that you understand it, that irrespective, how do you see, what topology do you see, as long as it is in series, all components are in series, you can rearrange them, you can shuffle them whichever way you want, and it's still going to be the same voltage at node A. That's it. So what will be the equation then? VS2 minus VA over R3 plus R4. That's the total current, I2. VS2 minus VA. Now, what will be different? If you keep the components like this, what will be different? The difference is going to be the voltage across R4 is going to be the same because same current is flowing, but this node voltage is going to be different here. This node voltage will be different here. If you move this down, then of course the node voltage here is going to be 5 volt. Then the node voltage here is going to be VS2 plus 5 volt. In this case, here is going to be I times R4 and then 5 volts. So at this node voltage will be same, but at this node voltage is going to be different if voltage source is on top and R4 is at the bottom. And if you switch it, this voltage is going to be different. But again, the total voltage is still going to be the same at VA, irrespective how you are arranging the components. All right, so that's going to give you VS2 minus VA over R3 plus R4. And then IX, of course, we already know, so we're just going to put IX, since we already know the value of IX, and that's going to be 0. VA is the only unknown here, so we're going to keep VA on one side and other things on the other side. So I'm going to take VA and this VA on one side, so it's going to be VA 1 over R1 plus 1 over R3 plus R4. When I take it on the right hand side, these two VAs, negative sign will become positive. And then on this side, what is left? VS1 over R1 plus VS2 over R3 plus R4 and plus IX. And since we need to know what VA is, then let's write down in terms of VA. VA is equal to Vs over R1 plus Vs2 over R3 plus R4 plus Ix divided by the multiple of VA, which is 1 over R1 plus R3 plus R. Let's calculate that. So in MATLAB, okay, so let's see what the values are. So Vs1 is 10, R1 is 200, R2 is 400, R3 is 600, R4 is 800, Vs2 is 5, and Ix is 10 milliampere. So these are all my values. And with these values, I'm going to calculate VA. VA is equal to Vs1 over R1 plus Vs2 over R3 plus R4 plus Ix divided by 1 over R1 plus 1 over R3 plus R4. 11.125. 11.125. Make sure you check, do it on your side and see if you get the same result. Sometimes parentheses can make difference. I can put incorrect parentheses and the result will be incorrect. So just make sure that you do it as well so you can confirm if the result is correct or incorrect. And make sure, as I said, make sure everyone should be doing it. Don't just look at it. Make sure you're doing it so that you get practice of using MATLAB, and it will help you during quizzes, during exams. If you just look at what I'm doing and you're not doing yourself, you're not going to get practice. Yes. I'm sorry. Simplification. Okay, let's go back to the simplification. All right. So check what. Mm-hmm. Mm-hmm. So you're taking VA because it's unknown. You're taking both VAs on the other side of the equation, right? So both are negative, so they're going to become positive.
Oh, it's
Mhm.
we're equal to 0.
Yeah. Mm-hmm. Yeah. Okay. So did anyone get the same answer? Same answer? Okay. So now we have Vx, and our Vx equation, as we know. Therefore, Vx is equal to Va plus Ix times R2, which will be R2, right? R2 is here. Yeah, R2. So let's calculate that. Vx is equal to Va plus Ix times R2, 15.125. 15.125. So that's my voltage across the current source. And observe the voltage across the current source is greater than Vs1 and it is greater than Vs2 as well. So in fact, the direction of I1 is going to be opposite because VA is 11 point something, 11.125, which is greater than 10 volt. The direction of I1 is going to be opposite. And likewise, direction of I2 will be opposite as well because, again, VA is greater than Vs2. So both I1 and I2, when you calculate them, according to the direction that I'm choosing, they're going to be negative values. That means the actual values are going to be opposite because VA has higher value than Vs1 and Vs2, but it has lower value than Vx. So the direction of Ix, of course, is the correct direction because we are putting that direction. Actually, we are putting that source. So that current is always going to flow in that direction. So develop concepts again. Calculation is easy. As you see, calculation with MATLAB, it's a breeze. But develop concept, develop analysis of the circuit. That's the most important thing. Once you can imagine the circuit in your head and, okay, this is what I have to do, this is how I'm going to do that, things are going to become very easy. All right, so what we need to know now, power. Power is simply product of voltage and current. And the power supplied by Ix is equal to EIX is equal to Vx times Ix, which will be 0.1512 watt or 151.2 milliwatt. 0.1512 watt or 151.2. So that's your power supplied by Ix. We use nodal analysis. We decided that mesh analysis is going to take longer because it will have more equations. So nodal is the way to go. And the first thing you figure out is how to calculate power. What do you need to get the power, and then how you're going to get that voltage across the current source. All right, guys, any question that you may have? 6, 7, 8, 9, 10. Okay, everyone is here. Quiz is going to be on Wednesday, remember. You're submitting your homework on Wednesday, so quiz is going to be Wednesday. And I see a lot of improvement over the pre-assessment that I gave you last week because I hope it's going to be improvement. I hope all of you will apply Ohm's correctly this time. Okay, so that's problem number 1 for today. If there is any question, please go ahead and ask me. I don't think I need to put any MATLAB work because it's simple. I'm just solving the equations and results are here. Anything that is not clear in this problem? Everything is clear? Okay. Yes, go ahead. Oh, yeah. There you go. I mean, if you want, I can put it. It's not gonna be any. Let's go ahead and snip that. Snap. Paste. So MATLAB work is here. Yeah.
The denominator of the 1 over R1. That came from
Equation. The equation that you have, look at the equation, right? So your equation is this right here. This is your equation for nodal analysis. So you have Vs over R1 minus Va over R1 plus Vs2 over R3 plus R4 minus Va over R3 R4 plus Ix. Yeah, just a simplification of that equation. That's about it. Yes, Eunice? Yeah. Node voltage is always measured with respect to ground. Potential difference is measured across a component. Node voltage is always measured with respect to a reference. Reference in our case is always ground. Yeah. If you want to measure potential difference across R3, that's going to be the voltage drop across R3, VA minus whatever the voltage on the other side. But if you just want to measure any voltage at any node, that's going to be that voltage with respect to ground always, reference. Okay, so let's go ahead and do another problem. Let's start with the next page. I'm sorry? So MATLAB work is here. Check your work against my work. See? It's just maybe some parentheses. Check your parentheses. Maybe some parentheses is not as missing or something. And check your values as well, just to make sure if you put the correct values of all the variables. I'm assuming it might be a parentheses. Well, usually if your parentheses are imbalanced, it should give you an error though. Okay, let's see. Let's see this question. Okay, we can do this. 1, 2. All right, let's do this. -1, 4 ampere. I think this is a question from the book, I believe. One of the editions. I don't know which edition. Because I usually don't take register value 1/2 and stuff. I did this. It's one of the problems that I did last time when I taught it. Assuming it's from is from the book. Okay. So this is the circuit. And the question is determine I'm specifying over here use nodal analysis for a reason. So we have to figure out what is the voltage across each current source. So we are trying to figure out what is this voltage. Let's call it VS1. And what is this voltage? Let's call it VS3. VS1 is across IS1, assuming this is ground. And VS3 is across IS3. And those are the node voltages. Let's call this node 1 and node 3. Now, if I give you this problem and I don't specify which method do you have to use, which method would you prefer? You're gonna, okay, node mesh, by mesh. Yeah. So that we know the current in those meshes. So we have two loops or two meshes, the middle one and the top one. It might be easier to go for the mesh analysis, I would say. As far as node is concerned, you have, of course, two nodes, but this is the case of pretty much supernode, if you remember supernode. But we are going to do it without supernode, and then we're going to apply supernode. We're going to do both ways. But if you do it without supernode, then you're going to have three equations, because you will also have to write the equation for the current that is passing through VS2. And you're going to take that as an unknown quantity, basically, because there is no resistance. So we cannot write down the current passing through VS2 in terms of Ohm's law, because we don't know the resistor in that branch, right? So that's going to be an unknown quantity for us. So that's if you're not applying supernode. If you apply supernode, then you can eliminate basically that node and write one equation for the currents going towards VS1 and VS3, and we're going to do that as well if you forget about supernode. But anyways, I would personally do mesh analysis for this because it's just going to be easier to do it. We already know the current here, which is 4 ampere in this branch, in this loop. We already know the current in this loop, which is 9 ampere. I can write the mesh equation for here, and I can write the mesh equation for the top loop and solve for those, calculate the current, and once I have the values for the current, I can easily find what is the value of VS1 and VS2 using simple addition of voltages like we did last time. But if you want to know what are the voltages directly, then of course you will have to apply nodal analysis. That will give you the values of those two voltages directly without any additional step after applying mesh analysis. Because mesh analysis is not going to give you voltages, it's going to give you, remember, currents in each of these meshes. But if you do have the values of current, then you can find VS1 and VS3. Here I'm asking you to apply the nodal analysis. So first we're going to apply the regular nodal analysis, then we're going to apply, we're going to do it using supernode. So regular nodal analysis requires us, or even the supernode, it requires us to first apply, assume currents either going away or going towards, whatever you want to do. Let's assume current in this branch is going away. Let's call this I2 or IR2. Let me just call this I2. The current in this, let's assume going away from VS3. Let's call this I3. We already know the current IS1 going towards, IS3 going towards. Now, don't forget that you have to write current in this branch as well. And let's call this IS2. And let's assume it is going from VS1 to VS3. And finally, let's say this current is I1. Okay. Now, common mistake, which is a quite common mistake, is when you're writing the equation for mesh analysis or nodal analysis. Remember, in mesh analysis equation, each of the term, it represents voltage. You're adding voltages, right? You're applying KVL. Now, what I have seen sometime that when a student sees a current source, in the case especially for super mesh, they just write that current source and add it to the different voltages in the loop, which is incorrect because you cannot add current and voltage together. All of the terms should be voltage terms. So please be careful about that. And likewise, when you're applying nodal analysis, all of the terms in the equation should represent current. So make sure that all of them are current. You're not putting, for example, you're not putting VS2 as one of the terms in the nodal analysis equation because VS2 is a voltage, it's not a current. So you have to assume a current that IS2 is flowing through VS2 and you have to use that value in the equation so that you are adding up all the currents. You're not adding currents plus voltage because those are different quantities. So nodal analysis equation, always keep in mind all the values should be current in the nodal analysis equation. And for mesh analysis, all the values, all the variables should represent voltages. Okay, so at node 1 KCL, we're going to apply. KCL at node 1. All right, what is the KCL equation at node 1? Who's going to tell me? Very good. IS1 equals I1 plus IS2 plus I2. One current going towards, three currents going away. Okay, so let's write this down. IS1, we already know the value. That's a known quantity, so we're not going to touch that. I1, what will be the equation? Equals, not plus. What will be the equation for I1 in terms of Ohm's law? I'm sorry? No, I1 is greater. Yeah, so VS1, let's say it again. No, look at the direction of the current. You have to look at the direction of the current. Yeah. Current is going from VS1 towards VS3. So you have to do VS1 minus VS3. You're doing opposite. You're doing VS3 minus. Always go with the direction of current. If you would have chosen the direction of current to be going towards VS1, then yes, VS3 minus VS1. But right now, the current that I'm showing, and make sure when you're solving any problem, you must show currents on your circuit. That, okay, I'm assuming current in this direction. Because if you write without showing the current, then how would I know which direction you're showing, for which direction you're applying the Ohm's law? So always show the current and stick with this direction of current. Do not change it for different nodes and stuff. Just always stick with this direction of current that you're choosing and write the equation according to that. So right now, it's going to be VS1 minus VS3 because current is going from VS1 node to VS3 node. So VS1 minus VS3 divided by the resistor value. All right, IS2 we already know. And I2. Oh, IS2 we don't know, sorry. So we're going to write down just the variable IS2 because we cannot write IS2 in terms of Ohm's law. So we're just going to write down as an unknown variable. And what about I2? I2, of course, we know, right? No, I2, we have to write the equation for I2. What is the equation for I2? Okay, so Vs1 over R2, Vs1 minus 0 over R2. Okay, so let's rearrange that. All the knowns on one side, all the unknowns on the other side. So all the unknowns, we don't know Vs3 and no, we know Vs2. Vs1, Vs3, so Vs1 and Vs3 and Is2. Actually, it's already all the knowns on one side, all the unknowns on the other side. I'm just going to rearrange it quickly. So Vs1, 1 over R1 plus 1 over R2. 1 over R1 from the first term and 1 over R2 from the second term. So that's the coefficient of Vs1 minus Vs3 over R1 plus Is2 equals Is. Because when we are solving for the three unknown quantities, then of course we have to make the matrix and we need the coefficient of each unknown quantity. So we have Vs1, coefficients are these, Vs3 coefficient is this, and then Is2 coefficient is 1. All these three values are unknown right now. Is1 is the only one that we know. Okay, so now KCL at node 2. All right, what will be the KCL equation at node 3? Sorry, not 2. Okay. KCL at node 3 with the voltage Vs3. What will be the KCL equation at node 3? Is2, okay, plus Is3, okay. Very good, excellent. So I1, Is2, and Is3 all going towards node 3, and I3 going away from node 3. So I1 plus Is2 plus Is3 equals I1 plus Is2 plus Is3 equals I3. Yes, there's a discussion question. Yeah. Yeah, because I'm taking this node 3, the voltage is Vs3. That's, yeah. Yeah, I'm just giving this node as node 1 and this node as node 3 because of the voltage designation, Vs3 and Vs1. It's just a label. It's just a label. Yeah, you can do 1, 2, you can do whatever. Okay, so I1, what is the equation for I1? Yes, I1 is? Why? Look at that. Look at the direction of I1. Yeah, keep repeating this. I keep repeating this. Look at the direction. So I1 is going from Vs1 to Vs3. So Vs1 minus Vs3 over R1. Once you assign direction, you don't have to change it. So make sure once you put together the circuit and you're applying nodal analysis, make sure you assign direction of current through each branch. When you are applying mesh analysis, make sure you assign loop currents for each mesh and stick with those directions. You don't have to change it throughout the problem. Just stick with those directions. Okay, so Vs1 minus Vs3 over R1. So Vs1 minus Vs3 over R1. Is2 is unknown, so I'm going to keep it as Is2. Is3, we already know the value of Is3, so it's going to go on the other side of the equation. So I'm going to keep it right now here and then take it on the other side in the next step. Okay, I3, what is I3? Vs3 over R3. Yeah, Vs3 minus 0 over R3. Okay, so so the unknowns are again Vs1, Vs3, and Is2. So let's write them down for our equation number 2. So Vs1 1 over, actually that's the only VS1, so I don't have to show that as brackets. So VS1 over R1, and then VS3, and this VS3. I'm going to take this VS3 on the left side of the equation. It's going to become negative, minus VS3, 1 over R1 plus 1 over R3. Both terms are going to be negative when I take this on the left side of the equation. IS2 is unknown, and I'm going to take the known quantity, which is IS3, on the other side of the equation. That's going to become negative IS3. And that would be our equation number 2. Anytime you have any question, please make sure to ask. All right, 2 equations, 3 unknowns. We need one more. Yes, go ahead. Because I3 is passing through R3, I'm assuming, right? So I3 is passing through R3. So the voltage here is VS3 and the voltage here is 0. Oh, equals because it's going away from node 3. Look, this current and this current, this current and this current, all going towards node 3. And this is the one that is going away from node 3. That's why. Yeah. All right. 3 unknowns, 2 equation. That means we need one more equation. Where that equation is going to come from? We need one more equation to solve for the 3 unknown variables from 3. You cannot solve 3 unknowns from 2 equations. So where the third equation is going to come from? Right, but what will be that equation? Who's going to tell me that? What is VS2 in terms of VS1 and VS3? If you want to write down the expression for VS2 in terms of VS3 and VS1, what that expression is going to be? Exactly right. So that's the third equation. VS3 minus VS1 is equal to VS2. Look at the polarity of VS2, of course. The potential difference that VS2 represents is from VS1 to VS3, positive. That means it is VS1. No, you said VS3 minus VS1. No, sorry. VS1 minus VS3 is equal to VS2. VS1 minus VS3 is equal to VS2. Also, VS2 is equal to VS1 minus VS3. And that is our equation number. Of course, IS2 is 0. The coefficient of IS2 is 0 in there. So we have 3 equations. We have 3 unknowns. Let's go ahead and solve them. Okay, my matrix A from the coefficients of VS1, VS3, and IS2. So let's see. Equation number 1. I have to assign the values of all the variables first. Let's assign all the variables. So IS1 is equal to 4. IS3 equals 9. VS2 equals 5. R1 1/3. R2 1/2. And R3 1/6. These are all the values. So my coefficient matrix for the 3 unknown variables from equation number 1. For VS1, I have 1 over R1 plus 1 over R2, Vs3 negative 1 over R1, and Is2 1. From equation number 2, Vs1 1 over R1, Vs3 negative 1 over R1 minus 1 over R3, and Is2 again is 1. And equation number 3, Vs1 is 1, Vs3 is negative 1, and Is2 is 0. So this is my coefficient matrix. And my constant vector on the right hand side from equation number 1 is Is1. So Is1 from equation number 2 is negative Is3, negative Is3. And from equation number 3, it is Vs2. And it's a vector, column vector. I made a row, so I'm going to put apostrophe to make it a column vector instead of a row. That's my column vector. Therefore, my unknown x values. Now, x, why I'm putting x? Because there are two voltages and one current in the unknown matrix. So x is a backslash c, or inverse of a times c, whatever. First two values are voltages, Vs1, Vs3, and the last value is the current, Is2. Let's go ahead and put this so everyone know that this is what we are doing. These are the three unknowns. Okay, so far if you have any question, then please go ahead and ask. And of course, these are the unknown quantities that we are looking for, right? We were looking for the voltages across the source 1 and the source 3. So those two values were the one that we were looking for. Got it? Good. Any question? Now this is without applying supernode, remember. We can apply supernode and then take a break actually. But in the meantime, if you have any question about this, you can ask. Yes, Rizal? You have a question? There's no really code. I mean, it's just calculation. It's not really a code. It's just calculation. Apostrophe, you mean? Or commas between the values? For C or for A? Oh, the square bracket?
Yes.
That's to define a matrix. That's to define a matrix, yeah. Matrix or a vector. Yeah. No. Parenthesis, no. To define matrix or a vector, you use squared bracket. Yeah. All right, guys. Any question about this problem? And once you have, and again, once you have the values, you can calculate anything. You can calculate power. You can calculate unknown currents or whatever. Doesn't really matter what you're calculating. You just need those values. So Is2 direction is opposite. we chose the direction that the current is going into the positive side. It is opposite. That means Vs2 is supplying power. It is not absorbing power because the positive current is coming out of the positive side of Vs2. Likewise, Is1 and Is3 are also supplying power because Vs1 is positive as well as Vs3 is positive as well with respect to ground. So all three sources are supplying power. Let's do the same problem without using with supernode. So when do you see that a circuit has a supernode? The circuit has a supernode if you see this condition, that you have a voltage source between two nodes, but there is no resistor. So you cannot apply Ohm's law to write down the value of current passing through that source. In that case, that's a case of a supernode, that you cannot write the equation for that branch in terms of Ohm's law because you are missing a resistor in that branch. It's only the voltage source that is there. Because if you do put a resistance there, then you can easily write down the equation for your through using Ohm's law basically. Okay, so let's see. So for supernode, what we're going to do, we're going to ignore that branch momentarily, and we are going to write down the KCL equation at node 1 and at node 3 in the same equation. It is basically coming from here. KCL at node 1, remember we have Is2 here, and KCL at node 3, we have Is2 here, right? So in fact, we can write this equation down, this equation in terms of Is2. Is2 is equal to Is1 minus I1 minus I2. And from this equation, we can write down Is2 equals I3 minus I1 minus Is2. Right? So basically, you can eliminate Is2. You can equate those two equations, and you can write down Is1 minus I1 minus I2 is equal to I3 minus I1 minus Is3. So Is2 is just going to be eliminated. And that's what supernode is basically. It does not consider Is2. It does not consider the current passing through this branch. What it says is, at node 1, write down the equation ignoring Is2. So we have Is1 going towards, Is2 and I1 going away. So Is1 minus I1 minus I2 on one side of equation. Basic. Yes. I'm sorry. We're just ignoring that current altogether. We assume that branch does not exist. So basically, you're ignoring that. And after you ignore that, in just one line, you're going to write the expression for both node 1 and node 3. On one side of the equation, you're going to write down node 1. On the other side, you're going to write down node 3. Or you can just say, if the current is going towards node 1, you're going to write down on one side of equation. For example, Is1 is going towards node 1. And in the other equation, what is going towards node 1? Is3 is going towards node 1. I1 is going towards node 1. So Is3 and I1. So you can write all the currents that are either going towards node 1 or node 3 on one side of the equation. Add them together. And all the currents that are going away from node 1 and node 3, right on the other side of the equation. So although they are two different nodes, but when you're applying supernode, you can just write down the expression as the sum of currents going either towards node 1 or node 3. and sum of currents equals to sum of currents going away from node 1 and node 3. Because again, if you equate these two values, IS2, you're going to write down IS1 minus I1 minus I2. IS1 is going towards IS1 and I1 and I2 are going away. And in the second one, IS3 and I1 going towards, and I3 is going away. So if I write down all the currents going towards I1 and I3, IS1 is going towards, plus I1 is going towards, and IS3 is going towards. And all the currents going away, I1 is going away, I2 is going away, and I3 is going away from node 3. So let me write this down so you don't forget. Write down all the currents going towards node 1 and 3 on one side of the equation, and going away. My and is pretty bad. Looks like R. Let's change that. And going away on the other side of the equation. So using supernote, first ignore IS2, basically. So this is what we are going to do. So our first equation is going to be currents going towards node 1 and node 3. So IS1 plus IS3 plus I1, because we have to ignore IS2 anyways. So IS1 going towards node 1, and I1 going towards node 3, and IS3 going towards node 3. So IS1 plus IS3 plus I1. IS1 plus IS3 plus I1. And the other three currents are going away either from node 1 or node 3. So I2 is going away from node 1, I3 is going away from node 3. Actually, there are only two currents, right? Or is there any third current? No, I1 we already considered it's going towards node 3. Oh, you're talking about it's going away from node 1. Yeah, so I1 plus I2 plus I3, because I1 is going away from node 1. So I1 well, I1 is going to cancel out then on each side. Let's look at these equations. IS1 minus I1 minus I2 is equal to I3 minus I1 minus IS3. So I1 and I1 will be cancelled out on each side of the equation. As you can see, we don't really have to consider this because they're cancelled out. So your equation is going to be reduced to I2 plus I3 equals IS1 minus IS3. All right, what is I2 in terms of Ohm's law? Vs1 over R2, and I3 is Vs3 over R3. Vs1 over R2, Vs3 over. That's going to be equation number 1. Where? IS1 plus IS3, yeah. Plus IS3, all right. That's our equation 1. And then for equation 2, we're going to do the same thing as we did to write equation number 3 for without supernode. That is, the difference between the two voltages is the source voltage. So Vs1 minus Vs3 is equal to Vs. Also, Vs1 minus Vs3 equals Vs. So with supernode, we will end up with two equations in terms of only node voltages. It's not calculating the current passing through the source Vs. Since the values are not changing, I'm not gonna change anything. Or I can actually, hold on. Let me do clear, and then let me recall the first line. Okay, so this is the first line, and then recalculate our equations. In this case, our A is from equation number 1 over R2 and 1 over R3 for the two unknown variables Vs1 and Vs3, and from equation 2, 1 and negative 1, 1 and negative. And our constant vector is is1 plus is3, is1 plus is3 from the first one, and from the second one it is Vs2. So that's our constant. So our unknown variables in this case is going to be just voltages. It's going to be A backslash C, 5.375, 5.375, and 0.375, 5.375 and 0.375. So same voltages we're going to get, but rather simpler way since we have only two equations. So this is how you're going to apply the supernode if you do have to apply. I personally don't really care what you're applying. I go for the easiest method. You need to go for the easiest method. Whatever is the easiest method, as an engineer, that's what you have to do. Easiest route. Engineers are inherently lazy, basically. That's why we invent things so that they can work for us, right? So make sure go for the easiest thing. As far as solution is concerned, whichever solution is easy, go for that solution. You need to know everything. You need to know what is super mesh, what is super node, what is this, what is that. Knowledge is always important, right? But you need to go for the easiest method. I mean, super mesh is very easy because if you're looking for only the two node voltages, super mesh is extremely easy. It's going to give you two node voltages using two equations. In this case, actually, I will apply super mesh. I won't apply mesh analysis. I mean, super node, sorry, super node. I won't apply mesh analysis because for mesh analysis, although I have two equations, but then I won't have the voltages. I will have the mesh currents. I still have to find the voltages using those mesh currents, right? So that's going to be a couple of more steps. In this case, for this problem, supernode is the best way to go because you have two equations written in terms of the unknown voltages, and solving those two equations, it's going to give you unknown voltages. So supernode is the way to go to solve this problem. Again, I can solve it any which way. I solve it two different ways, both nodal analysis. But I will use supernode to solve this problem for sure. Any question that you may have before we take a break? No? Okay. Let's go ahead and take a break. Let me stop recording real quick. Okay, guys. So let's see what should be the next problem. Let me open my old notes to see if there's something that I want to do from there. Supernode, we just did that. Okay, what is this problem? Let's see. Okay, let's do this problem. Let's go to the next page. Oops. So we have two dependent sources and one independent source. The independent source is the current source, 0.1 ampere. R1 is 10 ohm. R3 is 30 ohm. R2 is 20 ohm. And R4 is 40 ohms. And this dependent source is also a current source, 2 times VR3. And this dependent source is a voltage source, VD2. This is ID3. It's 2 times IR3. Okay, so what are VR3? VR3 is the voltage across R3. So the value of that dependent current source depends on the voltage across R3. And the value of this voltage source is the current that is passing through R3. So this current. All right, what is the question? So the question is determine the output power of each source. Use the easiest method to solve. Determine the output power of each source. Output power means power supplied. If it is power absorbed, then of course we're just gonna say that the power supplied is negative or positive power absorbed. And we have to use the easiest method. Yes. Okay, so first you have to determine to calculate the power supplied. Of course, you need two quantities. You need the voltage and the current. So for the current sources, you will need to find out what is the voltage source across each of the current source. And for the voltage source, you need to know what is the current passing through that dependent voltage source. So first establish that what you're looking for. That's the first step. The second step is how you're going to get those things using the easiest method. Now you say easiest is mesh. Elaborate why you think the easiest method is mesh. Okay, and why do we need? Why do we know those two currents? Huh?
Learning how IS1.
No, if in mesh analysis, you're talking about the mesh currents, and you said we already know two mesh currents, which is correct. But if someone asks you, okay, why do we know two mesh currents? What is your answer? Because the current sources are in the outer loop. So the loop current is going to be the current of the current source. That is correct. So that's going to be the answer. So we already know that the loop current in the top loop is ID3 and the loop current in the left loop is IS1. So we only need to know the current in the right one where the dependent voltage source is. So that is correct. However, we don't know what is ID3 value exactly, but if we know what is VR3, then we can figure out what is ID3 value. So that's not an issue. So yeah, let's go ahead and apply mesh. I think mesh is going to be easier method. However, after even applying mesh, and mesh is going to give you the current value, this current value, and of course we can calculate the ID3 value. We will still need to figure out what is the voltage across ID3 and what is the voltage across IS1 in order to calculate power. So remember, your job is not going to be done if you apply mesh analysis and get the current in the loop where you have VD2. That's halfway done. You still have to go and find out the voltages across IS1 and ID3 in order to calculate the power supplied by those two sources. So again, analyze the problem and understand what you're looking for. So let's go ahead and apply mesh. By the way, if you apply nodal analysis, we have, of course, one node right on top here that we have to apply the nodal analysis, the KCL equation. We have a node right over here where we have to apply the KCL equation. We already know the voltage of this node, which is VD2, so we don't really need to apply the KCL at this equation because the voltage at this node is VD2. So if we are applying nodal analysis, we have two nodes with unknown voltages. Of course, this is a dependent source. So once we solve for IR3, we can find the value of this dependent source. But in the meantime, we can just use this node voltage to be VD2, that is 2 times IR3. But we don't have to write the equation for KCL at that node because the node voltage is VD2. Whether that node voltage is for the dependent source or independent source, we know that node voltage, that's VD2. So nodal analysis gives you two equations, mesh analysis gives you one equation. Let's apply mesh analysis. So let's go ahead and we know that the mesh current, this is IS1. Mesh current here is ID3. So this is the only mesh current that we don't know. Let's call this mesh current ID2 corresponding to VD2. Mesh analysis will give us one equation. Okay. So KVL in the mesh with VD2. So we're going to apply KVL in the mesh with VD2. All right, what will be the KVL equation? or mesh analysis, mesh equation for this mesh or this loop? Who's going to tell me? Okay. ID2 multiplied by R4 plus R3. Okay. What else? You're kind of messing with signs a little bit. Now, IS1 and ID2 are flowing in the same direction through R3, but through R4, ID2 and ID3 are in the opposite direction. So if you're writing the equation for the mesh here, now it's going to be add up IS1 and ID2, but ID3 is going to be opposite, so that's going to be negative. So the mesh equation is going to be the voltage source VD2 equals ID2 R3 plus R4, R3 plus R4 plus IS1 R3 minus ID3 R4 because it's opposite to ID2. So that is going to be IS3, right? ID3, sorry, ID3. ID3, yeah. ID3 R4 or ID2 R3 plus R4 plus IS1 R3 minus ID3 R4 equals VD2. All right. Does this equation look good to you? Yes. Is that R2 or something else? R3? IS1 R3, yeah, thank you. IS1 and R3. All right, my question looks good. Or there's any question about that question? So the only unknown here is what? We do not know what is the current ID2 in this case. But first, we are going to write down the other values. For example, VD2 in terms of IR3. So VD2 is 2IR3. ID2 is of course unknown. IS1 we already know. And ID3 is 2 times VR3. Times R. Okay, so what is IR3? Who's going to tell me what is IR3? We don't know VR3. IR3 is what from that? Say it again. No, IR3 is not the voltage. IR3 is the current. What is that current? IS1 plus ID2, exactly. Remember, we are looking for ID2. So write it down in terms of ID2. So IR3 is 2 times IS1 that we already know plus ID2. ID2 is what we are looking for, right? ID2, R3 plus R4, IS1, R3 minus. All right, now VR3. VR3 is, oops, VR3 is no, not over. VR3 is IR3 times R3. And IR3 is, like we just did, IS1 plus ID2. So VR3 is IS1 plus ID2 times R3. And that's what we're going to write down. So the equation is going to be in terms of only unknown ID2. So that's going to be 2 times IS1 plus ID2 times R3, and then R4 is right here. Right? 2IS1 plus ID2 times R3, 2IS1 plus ID2 times R3, and then R4 is coming from ID3 was 2 times VR3. ID3 is 2 times VR3. So from the dependent sources, we went ahead and plug in their respective variables in terms of the known values and the unknown value. And now our equation has only one unknown, and that one unknown is ID2. So we're going to put ID2 on one side of the equation. Everything else is going to be on the other side of the equation. So I have 2 ID2. I'm just going to write down ID2, 2 from here. And then I'm going to bring this on the left side of the equation. That's going to become negative ID2 times R3 plus R4. So minus R3 minus R4. And then I'm going to bring this ID2 on the left side of the equation. It's going to become plus 2 times ID2 R3 R4. So plus 2 times R3 and R4. So all ID2s are on the left side of the equation. And I'm going to take this IS1 on the right side of the equation, and it's going to become negative 2IS1, and rest is going to stay the same, plus IS1 times R3 minus 2IS1 times R3 times R. So ID2 is going to be negative 2. I'm just going to write down IS1 as a common factor. IS1 times R3 minus 2 times R3 R4 divided by this on the other side, 2 minus R3 minus R4 plus 2 times R3 R4. It's calculated. All right, let's go ahead and plug in the numbers first. Okay, what do we have? IS1 is 0.1. R1 is 10. R2 is 20. R3 is 30. R4 is 40. And those are all the known quantities. Of course, we don't know ID3 and we don't know V. And now our last equation is ID2 equals IS1 times R3 minus 2 times R3 plus R3 R4 times R4. IS1 times R3 minus 2 times R3 R4, all within parentheses, divided by 2 minus R3 minus R4 plus 2 times R3 times R4. Oh, that's 2 minus R3 minus R4 plus 2 times R3. So ID2 is negative 0.1017. That means the assumed direction of ID2 current is opposite. It's not the same direction, it's the opposite direction. Getting the same result? No? Okay. Oh, it's a type. Okay. So now power. Go back. To calculate power, we need to calculate the voltage across IS1, VS1, let's call this. We need to calculate the voltage across ID3, VD3, and we already calculated ID2. That we already have. But first, we're going to determine what is the actual value of VD2. Calculate IR3 basically, which is combination of IS1, ID2, and we have ID2 value. So let's go ahead and calculate the power supplied by VD2 first. It is actually power absorbed because the direction of ID2 is opposite. ID2 is negative. That means ID2 is actually going into VD2. But you also have to consider, because VD2 depends on IR3, so we have to consider if IR3 direction is this or its opposite. Because if the IR3 direction is opposite, then the polarity of VD2 is going to be opposite as well. And that will make VD2 to supply power instead of absorb power. So let's calculate both. What is the value of VD2 and then calculate the power. So power by VD2. Okay, so VD2 is 2 times IR3. 2 times IR3, and IR3 is 2 times IS1 plus ID2. Let's calculate that. VD2, no, that's not VD2. Yeah, VD2 is 2 times IS1 plus ID2. So a negative value. That means the polarity of VD2 is opposite. Therefore, it is supplying power, not absorbing power. That's going to be negative 3.43 millivolt. Negative 3.43 millivolt. Therefore, the polarity of VD2 is opposite, and it is supplying power since ID2 is coming out of the positive side of the supply. Okay, so P VD2 is VD2 times ID2. Both are negative. That's going to make it positive. All right, 3.48 exponent negative 4. So that's going to be 349 microwatt, approximately. 349 microwatt. So that's the power supplied by your dependent voltage source. We still have to find the power supplied by the other two. All right, if you have any question, make sure you ask me. Just make sure we are doing it correctly. VD2 is 2IR3. 2IR3 and IR3 is IS1 plus ID2. We calculated ID2 already, which is negative 0.1017 ampere. So opposite direction. Based on that, we calculated IR3, negative 3.43 millivolt, opposite polarity. That means power is supplied, not absorbed, 349 microwatt. All right, guys, any question that you may have about this so far before we move on to find the power of the other two sources? Let me see my MATLAB work. I can also copy this just to be on the safe side. So if we, it turned out if we did make a mistake, then at least. ID2 is this, VD2 2S1. All right, who is going to tell me now, looking at the circuit, how we are going to find VS1 and VD3? Anyone? VS1 and VD3. Okay. R3 and R1, yes, you can do that. So basically KVL in that loop, you're applying KVL in that loop. So to find VS1, we can simply apply KVL in this loop, or we just start from here and add all the voltages through this path and get to this point. That's going to be VS1. So let's do that. We have, so what will be the voltage at this node right here? What is VR3? What is VR3? IR3 times R3, and IR3 of course is IS1 plus ID2. And then what is the voltage across R1? No, not negative, because both currents are flowing through R1 in this direction. So here the voltage is higher and here the voltage is lower. ID3 plus IS1 times R1. So the voltage at this node, the voltage at this node is going to be it is going to be IR3 times VR3 plus IS1 plus ID3 times R1. And basically you're applying the KVL here. Negative VS1 plus IS1 plus ID3 times R1 plus VR3 is equal to 0. That's what you're doing. So let's go ahead and solve this. Voltage VS1. VS1 is IR3 times R3 plus IS1 plus ID3. Is that ID3? Come on. It's ID3 times R1. ID3 times R. Okay. IR3, of course, is IS1 plus ID2 times R3 plus IS1. What is ID3? ID3 is what? 2 times VR3, and VR3 is 2 times IS1 plus ID2 times R3. So the same thing as what we have right over here, IR3. So IS1 plus ID3, no, not ID3, IS1 plus 2 times 2 times what? IR3, R3, right? So IR3 is IS1 plus ID2 times R times R1, sorry, times R. So IS1 plus ID3 is 2 times VR3. Keep going up and back and forth. And it takes longer. 2 times VR3, and VR3 is IR3 times R3, and IR3 is IS1 plus ID2. So 2 times IS1 plus ID2 times R3. That's ID3. IS1 and R1. So that's my VS1. Let's calculate it. VS1 equals IS1 plus ID2 times R3 plus IS1 plus 2 times IS1 plus ID2 times R3 times S. That is not S, that's 2 times. And that's negative 0.80617. So the voltage across that source is coming out to be a negative value. That means the source is absorbing power, it's not supplying power. Since VS1 is negative, IS1 is absorbing power. Not supplying power, but absorbing power, because the current is coming out from the negative side of the power supply, where the potential is negative. It's coming out where the potential is negative. So how much power it is absorbing, or how much negative power it is supplying? P S1 equals Vs1 times Is, negative 8.06 milliwatt. Supplied or 8.06 millivolt absorbed. Negative power supplied is positive power absorbed and vice versa. Any question about this? Yeah. That means the current is coming out of the negative side of the battery or going into the positive side of the battery. So when the current is going into the positive side, that means the battery is being charged or the power is being absorbed. Yeah. If the current coming out of the positive side of the battery, then positive current comes out of the positive side of the battery, then the voltage source is supplying power. Otherwise, voltage sources or the source, simple voltage or current doesn't matter. The source is supplying power or absorbing power. Yeah. VD2 is different. That's the dependent source on the right side. And IS1 is the independent source on the left side. There are two different sources. VD2 is supplying power because, well, yeah, because ID2 is negative, but the polarity of VD2 is also negative. So actually, the direction is opposite for VD2. VD2 value is negative. That means if you put the VD2 source properly, it is going to be opposite with the positive value. Otherwise, it has a negative value. Or if you want to keep it like that, that's fine. The power supplied is ID2 times VD2. Both ID2 and VD2 are negative. That will make the power positive, which means actually the source is supplying power. It's not absorbing power because ID2 is coming out of the positive side of VD2.
Yeah, that's what they checked out.
So both ID2 and VD2 are negative, remember. That will make the power to be positive, which means that the direction of ID2 is opposite and direction of VD2 is also opposite. And ID2 is coming out of the positive side of the VD2 when you make the dependent source direction inverted. Yeah. Now the third source that is left is ID3. If VD3 is positive, that source will be supplying power. If VD3 is negative, that source will be absorbing power. How are we going to find VD3? Who is going to tell me? Exactly. You use KVL in that loop or the node voltage method, whatever. But yeah, you can use KVL in that loop. What will be the KVL equation? Let me write down on the board so I can copy it here. What will be the KVL equation? Don't use numbers. VD3 and what? No, that's not the KVL equation for that loop because you have in that loop you have R1, you have R4. If you're applying KVL, that's not the equation. Okay, so you're not applying KVL. You're just going from where to where. You're going from VS1 since we know the VS1. So you're going from VS1 to VD3. But remember, VD3, the other end is not grounded. You have VD2 source over there. So the voltage here is not going to be VD3. The voltage right here is not VD3. VD3 is across this source, which is the voltage here minus VD2. But you were telling me KVL. Okay, tell me the KVL equation. VD2 is not there in that loop. VD2 is not in the top loop. VD2 is in the right loop. So VD2 is not going to be part of the KVL equation because your VD3 is in the upper. VD3 is not in, right? Oh, it started with VD3. So start with VD3. ID3 R2 plus ID3. Put down all ID3s together because ID3 is going toward 3 resistors. ID3 is what? R? R1, R2, R4. R1 plus R2 plus R4. Okay. And what else? Plus IS1 R1. And minus ID2 R4. ID2 R4. Okay. So that is going to be your KVL equation in that loop. Or you can just start negative VD3, positive ID3 R2, positive IS1 plus ID3 R1, and then positive ID3 R4 minus ID2 R4. So it's going to be the same equation equals to 0. So that's going to be the KVL equation for that loop. And this is what we're looking for, VD3. Yeah, VD3 is not in these loops. VD3 is in this. And that's what you're looking for. To find VD3, apply KVL in the top loop. VD3 equals ID3 R1 plus R2 plus R4 plus IS1 R1 minus ID2 R4. We should have just calculated the value of ID3. Did we calculate the value of ID3 somewhere? We did not. Okay, because ID3 is what? 2 times VR3. Just keep going back and forth. ID3 is 2 times VR3 and VR3 is IS1 plus IS2. No, IS1 plus IS2 times R3. Let's go ahead and calculate that. ID3 is 2 times VR3 and VR3 is 2 times ID2 plus IS1 times R3. So negative 0.1029. So now we have that value. We don't have to go back and search. Okay, so VD3, ID3 times R1 plus R2 plus R4 plus IS1 times R1 minus ID2 times R4. So VD3 is coming out to be negative as well. That means that source is also supplying, absorbing power instead of supplying power. Let's go ahead and snip it. Snip. So power of D3 or PID3 is ID3 times VD3, and no, ID3 is also negative. That's why. So the source is supplying power. ID3 value is coming out to be negative as well, which means that the direction of that source is the opposite direction, because ID3 value is negative. So direction of this is opposite, and VD3 polarity is also opposite. So that source is supplying power. It's not absorbing. That as well. Supplied by ID3 VD3 equals VD3 times, and then I'm going to just put this connection use ID3. So 0.22 watt power is supplied. This is supplied. We have power absorbed. We already mentioned that. Negative power supplied, positive power absorbed. And the first one is supplied as well. So two sources, actually both dependent sources are supplying power, and the independent source is absorbing power. Pretty interesting question. All right, guys, any question that you may have? This is a fairly not a straightforward problem, I would say. So a little complicated problem. A little. No, it is no, not as straightforward. Well, if the problem is just to find ID2, then it's pretty straightforward. Well, once it comes down to calculating power, then other quantities that you have to calculate, that makes it a little more difficult, to be very honest. Yeah. Generally, I don't give those type of like extended problem in exams or quizzes. If I ask you when power is just going to be like calculate the power of just this source or something. So you have to do it for only one source. But again, remember, stick with the basic concepts of the calculation of power. You need, if it's a power supply, then of course you need both voltage and current of the power supply. If it's a resistor, then of course you can use I square R as well, or you can have voltage across the resistor and the current passing through that resistor, so you can have any. But for the power supplies, of course, you must have both current and voltage of the power supply to calculate power. If it's the only power supply, then you can calculate the power in all the resistors if you have just resistors, and the same amount of power is going to be supplied by that only source if you have that single source, because conservation of power is going to be there. So in this case, the total power supplied is going to be the power supplied by both the dependent source, and then resistors are going to consume power, and of course the source, independent source, is consuming power as well. So once you calculate the power of resistors and add all of them together with the power of this VS1, that should be equal to the power supplied by the both of the dependent sources. Yeah. Conservation of power should always be fulfilled, basically. So if you want to check, you can apply conservation of power. Okay, guys, it's 11:30. I wanted to start coming in. We don't have time, unfortunately. So I think everyone is here. So everyone is marked present. Let's go ahead and stop recording. And this recording and the notes are going to be posted, of course. We only did 3 problems, but again, the third problem took time.